Okay, so here's where we were last time. We were talking about Stokes' curl theorem. Reminder, the big idea with Stokes' curl theorem is it's just we're kind of ripping off ideas that we've already applied. We're ripping off ideas we've already ripped off and been successful in kind of reproducing theorems over and over again several times previously in different contexts. So that's a big point. We're taking the same ideas, applying them in different contexts. Here, with Stokes' curl theorem, we're looking at surfaces in R3 and their boundary curves. Right? Now, one complication of Stokes' theorem is both of these are oriented things. When you talk about a surface in R3, here let me color code. When you're talking about a surface, that comes with an associated orientation. If you want to talk about flux through that surface, well, you got to know which way. Right? So it's an oriented object. Likewise, that surface, according to a certain rule, that oriented surface, its boundary is another oriented thing. And what we're going to be evaluating on that boundary, namely a vector line integral, being as it is around a boundary, it's a circulation. That circulation has to be computed with an orientation. So this boundary curve needs to come attached with an orientation as well. So in this context, the rules for which way does it go, very sort of careful. You have to think about what is the orientation of the surface in order to ascertain what is the orientation of the boundary. And it's this whole right hand swirl thing. And I won't go through that again. We went through it last time. Okay. All right. Okay. We made the observation that this circulation accumulates. Well, golly, it looks an awful lot like the picture for Green's theorem. You can literally take a picture that you would have drawn for Green's theorem on a piece of paper, pick it up, and then kind of give it a little bend. Now you've got a 3D model for a picture describing how, in this context of surfaces and boundaries, that circulation accumulates. It's the same idea. Specifically then, on any given shared piece of curve, you're going to pass along that curve twice, once oriented that way, once oriented that way, respective of the orientations on the pieces of surface on either side. And so they cancel. Yes?
I just want to make sure I'm not confusing two topics.
Yeah.
Is Stokes a continuation of Green's in R3?
It's a different theorem. I like to think of them as different theorems. I mean, there's a lot of analogies between them. They're both looking at two-dimensional things. In R2, we think of it just as a region. In R3, we think of it as a surface. In both cases, there's boundary curves. Right? But the context is different. The resulting theorems, the way you write them down, is necessarily different because of the context. But you're quite right. There are some really strong analogies between them, and that's why I'm trying to draw this strong analogy. But so I would like to encourage thinking of it as an analogy or comparison, and not that they're literally the same theorem. Okay. Yeah, that's a great question. Thank you. Okay. So this is about where we were last time. We made the observation that circulation accumulates. Right? You write that down for if you chop your surface up into a bunch of pieces, the grand total, or I should say, the boundary circulation around the whole surface is the sum of the boundary circulations around the little pieces. So this first line here just says circulation's an accumulating quantity. Right? Multiply and divide by surface area, and you can kind of see this kind of coming. It's like, oh my gosh, it looks like a surface integral at this point. It's almost like we have the theorem worked out. The remaining question is to figure out what is this new notion of density that has arisen. We've found ourselves in this position several times in the past of, we turned it into an integral. Now there's an integrand, which we know is a density, and we just have to figure out what that quantity is. I have skipped in all the previous contexts the discussion of, how do you figure out what that thing is? And I've just said, it's details. And the more important thing is how to think of it as a density. I am largely going to skip the details here as well. But there is a twist, there's a complication in how to think of this as a density. The formula is a little bit weird. It's ultimately very natural, but we're going to have to kind of come at this a little slowly and delicately. Okay. So perhaps you noticed when we were talking about the fundamental theorem of line integral, I kind of gave you a little bit of dance around the idea of the density. Y'all remember that? I said, well, it's kind of, the gradient's not exactly a density because it's got a direction, and the density is really complicated because it depends on which direction you're going, and there was a whole sort of thing. Not so with the fundamental theorem of calculus. Fundamental theorem of calculus, derivative, that's the density. Nice and crisp. Not so with Green's theorem. With Green's theorem, Green's operator, it's the density. It's a scalar quantity. It's a super simple story. Divergence theorem. Divergence. Scalar quantity. That's the density. End of story. I want to go back to the fundamental theorem of line integrals and flesh out a little bit more about what do I mean by the density being an oriented density. Because ultimately that's the problem that's going to happen here. This thing here is what we're going to, well, it's related to an oriented density, and you have to think of it in a different way. So here we go. Let's start off with the much more relatable fundamental theorem of line integrals. Okay, change is the object we're interested in. You make the observation that change accumulates. It's an accumulating quantity. Write it as a limit. Write it as a sum. Write it as a limit, and multiply and divide by size. Our usual game. We end up with something that looks like an integral. Scalar line integral. Here is our density. Right? That's the thing that you multiply size to get quantity, namely change in this context. And the awkwardness was that density, change density, is not the same as the gradient. Right? The gradient's just a little bit more complicated of a thing here. I mean, the gradient is in a way, the gradient is kind of sort of telling you change per unit distance, right? You could imagine, by the way, that, maybe these lines, maybe these level sets that I have drawn here to, help you visualize the function, maybe those are level sets of altitude as you climb up a mountain. Well, the length of the gradient tells you how steep it is. What is the change density of altitude per unit distance traveled? And sure, you can talk about how steep the mountain is. But unavoidably, mountains are steep in a direction, right? It's steep as you're going that way. If you're going in that direction, then what you experience as change per unit distance is how steep the mountain is. But if you're going this way, you have a very different experience, right? Right? So the gradient just doesn't tell you the whole story by itself. It can't. Change is unavoidably in a certain direction. Right? So the gradient has to be a vector in order to encapsulate that. Right? And then specifically, it's by dot product with your actual direction that you're going that you get your actual change density. Right? So if you're going straight uphill, then the altitude per unit distance is your dfds. If you're not going uphill, you don't have the same dfds. Does everybody see what's going on here? Okay. Questions? Okay. So the name that I give to the gradient vector here is, I like to think of this as being something called oriented change density. This gradient vector is telling you two things. It's telling you how steep the mountain is. Sure. It's telling you altitude per unit distance. Change per unit size of the domain, however you want to say it. It is telling you a density, but it is specifically telling you only the density in that direction, but then it's also telling you what that direction is by virtue of the fact that this is a vector, not a scalar. It's giving you how much change per unit distance and in what direction is that change per unit distance happening. Right? Now, then if you should decide, as the circumstance we find ourselves in, as we're moving along, let's say a curve like this, if you find yourself moving along and you want to know, yeah, but I'm not going uphill. I'm going along this other curve that's so much more gentle in its steepness. Right? How much change per unit distance am I going to experience? Oh, well, you've got to do the whole dot product thing, and that dot product in yellow there is your personal experienced change density. Everybody on board? Okay. All right. This is in strong analogy with what's going to happen in this Stokes' theorem context. So I'm going to be flipping back and forth between this page and this next page where we're talking about Stokes' curl theorem. The analogy is very strong. So let's start off with, what is it that we're actually measuring? Here we were measuring change. We represent the change by these level curves. So the function's increasing, but the function's increasing in a certain direction. Okay. Oh gosh, I didn't mean to delete the thing there. Sorry. Okay, it's changing in a certain direction. With Stokes' curl theorem, we're not measuring change. We're measuring circulation. Right? So here's the thing that we're measuring the circulation of. This vector field here. Oh, it's hard to draw this vector field. So please use your imaginations and visualize we have a vector field here that's representing a flow that's kind of like this. It's got imagine a sort of a sideways tornado kind of a situation, right? There's a flow kind of around that line. Does everybody see what we're talking about there? Okay. So let's, in the same way that we could ask here, our function is changing, and it's changing in that direction. Analogously, let's talk about the circulation here. Yeah, there's circulation. Look at it. It's all spinning and stuff. Right? The fluid is clearly spinning. But it is not just spinning in a scalar sense. It's spinning a certain way. The spinning is specifically around this axis. Right? So you're going to notice that if you look at circulation around that way, right? So in other words, again, it's hard to draw the picture, but if your fluid is flowing around like this, and if you are moving around a curve that's kind of, if you will, going around the same way, right? Then you're going to notice a lot of circulation. The vector field is going along the curve as you go around the curve. Yeah. Okay. So that's analogous to this picture over here. If you are going in the direction that the change is actually happening, then yeah, you're going to experience change for sure, right? But if you are going in a direction that's well, let me be deliberately sloppy here. That importantly different direction. Right, then you're not going to experience that change. And along those same lines, let's look at this other picture here. Now, this was my attempt to draw the exact same vector field over here. Right, so the same sort of, the fluid is flowing around like that. Now let's visualize, well, what happens if you're going around like that? And think about, now this is a hard hand gesture to do, but if your fluid is flowing around like this, and your curve is going, I don't know if I can do them both at the same time. If this fluid is flowing around like that, and your curve is going around like this, there's an incompatibility of sorts. Let me draw some field lines. The field lines over here at these points are going that way. Right, and then they kind of go over and down, and then when you get over to these points over here, they're kind of going this way, and the fluid is just not flowing along the curve. Line integrals measure how much the fluid is flowing along the curve, not perpendicular to the curve. That's not what line integrals do. So no circulation. Okay, so the picture is harder to draw. It's harder to visualize because it's three-dimensional and such, right? And it's a vector field instead of, just a scalar valued function that has level sets that I can just kind of see, right? So it's geometrically more challenging, but the analogy is very strong. If you are going the right way, you will experience here the change, here the circulation. If you are going what I'm going to loosely call the wrong way, right, like this, you will not experience the change in this context. You will not experience the circulation in this context. Okay. All right. So, how do we make this precise? Well, again, we're not going to. The details are not. I don't think in this context particularly helpful. So, how do we get our hands on this? Well, there is a vector, again, that tells us not only how much changing is happening, but what is the direction that the change is happening. Analogously, here in this situation, there is a vector that tells us by its magnitude how much of a vortex, how much of a tornado is, how much spinning, if you will, is the fluid doing, but also by virtue of its direction shows you in what direction is that spinning happening. Specifically, it indicates the direction by virtue of pointing in the direction of the axis that the spinning is happening around. Yeah.
But why does the vector field look kind of like tornado?
I'm sorry?
Why do you draw the vector field like that?
Well, I'm just as a for example. I mean, so for example, I mean this function over here. I'm drawing level sets of an altitude function just so I can have an example. I'm drawing an example of a function that's changing so that I can help. So I can have some context in which to talk about how we're going to quantify change. So I draw a picture of change to quantify change. Here I'm drawing a picture of circulation so I can, numerically represent and figure out how to talk about circulation. Yeah. Right. Okay, so the gradient plays a role in describing the circulation, again in an oriented fashion. Color coding. The circulation density, how much circulation per unit area is given by the magnitude of the curl. The direction that this circulation is happening is given by what I call the orientation of the curl, the direction that is that the curl is pointing. Okay, very strong analogy. By the way, the formula works out to be the same as well. When I say that this oriented circulation density does this in the following way, notice it was by a dot product of the oriented change density with your direction vector that gives you your change density. Likewise here, it is by a dot product. Let's see if do I have the picture? No. I'm gonna have to, I guess it's fine. It's by a dot product of the curl, the oriented circulation density, and the orientation of that which your path that you're circulating around. We represent that by the normal vector of the little piece of surface whose boundary we are going around. That dot product is what gives you your circulation density. The analogy is very strong. Dot product with your orientation is what turns an oriented density into a density. Same in both cases. Okay, now, why is this true? Details. Don't worry about it. You don't have to deal with that. I think the far more important thing to digest and internalize is that's what this computes. Curl is the thing that lets you measure how much the circulation, the flowing of the fluid is actually flowing, around your boundary as opposed to, not around your boundary at all. Okay. All right. Okay, so plugging that in. Here's that formula that we just wrote down. Circulation density is computed as a dot product of your oriented circulation density with your orientation, just like in the fundamental theorem of line integrals. So our previous surface integral, now notice this was developing into a surface integral. By the way, you might have noticed, I don't know, maybe you didn't, probably didn't, but that's fine. Notice this is seemingly a scalar surface integral. That wasn't what we were sort of hoping for. Look down here at our diagram. Right in our diagram, here's the context of our diagram and what we're looking at. We were kind of hoping and expecting that our circulation would turn into a vector surface integral. Right? If the pattern's going to fit, if all these joints or dovetails are going to just perfectly fit together, shouldn't it have been a flux? How come we're looking at a scalar surface integral here? Anyway, that could have been a worry. Well, check it out, because this circulation density had an orientation connection. Notice that we do now, in fact, have in ds, well, more to the point, dot in ds, therefore dot ds, and therefore this is a flux. And so the pieces just keep fitting together perfectly. Everybody on board? Yeah.
For finding that normal vector, if you have a surface,
yeah,
and the vector was pointing towards you, should the fluid be flowing counterclockwise?
So there's the orientation is about telling you what direction, when you're doing a flux integral, what direction the integrand of your flux integral is pointing. Here's what's really confusing about this story is we have two oriented integrals here. Here is our original line integral, and notice the integrand is a vector field. Right? This is what we're taking circulation of. Awkwardly, then come over here and notice that now we have another integrand that's a vector field now of our flux integral. Right? And what's very confusing is, well, we have two different vector fields, and which one do you think of as being a fluid? And kind of both. Gosh, this is terrible. But so we have this red, highlighted in red there. We have a fluid that's flowing around that we're trying to keep track of. How much is it circulating? Right? This blue field is going sort of, if you will, if the circulation is like this, then the blue field is kind of going like that. Algebraically, it's a flux that computes that circulation, but you shouldn't really think of this as literally being a flux of a fluid. Think of this as just an algebraic calculation that's a tool for computing the line integral that we're actually interested in. Yeah, so just think of it algebraically. Yeah.
Does that vector that's curl of that, does that stay like the same direction?
No, that's the weird thing, is it doesn't necessarily. So these pictures that I drew here, just to kind of simplify things, I was drawing little pieces of surface that were flat, right? But you could well imagine how, over a larger surface it's going to be all bumpy and wiggly, and the normal vectors are going to change direction. But then yes, you're quite right. The fluid flow whose circulation we're interested in is not going to be just a simple little picture like that. And it might, think of a tornado, right? Tornadoes get all kind of weird and kind of, they change directions, and over here maybe there's no airflow at all, and then over here is real tight airflow. The direction of the direction and magnitude of the curl will change dramatically. Yeah. Right. Okay. So it all fits together. Finally, keep in mind what we were doing here. We were looking at a vector field. We were looking at circulation of a vector field around a boundary of a surface. That's where we started. And what we found is that we could write it as a line integral. A surface integral. Initially didn't look like a flux, but it ended up being, per above, a flux of this thing called the curl of the circulating vector field. Notice the pattern. It's exactly the same as all of our other theorems that we've seen here. Okay. I, of course, am a big believer in, don't just look at the theorem written down as, okay, this algebra equals that algebra. Try to make sure to, digest a certain amount of intuition of what's going on here. That the object that we are interested in here is an accumulating quantity called circulation. It accumulates in a way that's morally equivalent to the way that change accumulates and to the way that boundary flux accumulates. It's an accumulating quantity, and it is computed as an integral over the entire surface of an associated density. Okay. All right. Okay, so let's get our hands dirty. Let's do one. So let's compute a line integral. The vector field here is given. The curve over which we are computing this line integral, that curve is given. Got a vector field, got a curve, compute the line integral. Now you've got a lot of options here. One thing you could do is plug and chug, right? You can in fact, look at this curve has already been parameterized. It's like it's begging you to plug and chug. Right? And remember that a parameterization means that that's x. And that's y, and that's z, and you can just plug that in straight into there, and f dot x prime dt and all that. And notice that does look like it'd be kind of nasty, right? We're going to have e to the power of sine t. I mean, it's doable, and it would, maybe it'd work out, but it's not your first choice. Okay. So then you say, oh, hey, but yeah, so this is a line integral. How about the fundamental theorem of line integrals? Right? That'd be nice. Fundamental theorem of line integrals seems like it's easy to work with. All you have to do is find the anti-gradient, and then bam, right? Problem. This vector field does not have an anti-gradient. And you can see that a couple of different ways. One is you can play the game and lose, right? Which you would, because there is no anti-gradient, I claim. The other thing you can do is use the lifetime theorems we talked about a little while ago. You can compute the curl of this. And the curl of this is simply not 0. Now, I encourage everybody to do that calculation. Just, make sure that you're clear on how to look at a vector field, find the curl, and thereby infer appropriately whether there is or is not an anti-gradient. Okay. In this case, there's not. Okay. So, last option, I suppose. Well, one of our last options. Stokes' curl theorem. This theorem right here says that if you want to compute a line integral, you can compute that line integral by instead computing this flux. Do, however, notice that there is an asterisk. This does not work just all the time. This only works in a special circumstance. You can see it right here in the statement of the theorem. This only works if you're looking at a special line integral, namely a line integral over a curve that is a boundary. Reminder, this is not a mere sort of formality mathematicians get uptight about, certain, little delicacies, right? That is not what's going on here. The curve has to be a boundary of a surface because you need to know what that surface is. That surface is the domain for your new flux integral. If your curve is not a boundary, this makes no sense at all. This is meaningless garbage if your curve is not a boundary. Now? Okay. All right. Okay, so we better look and see. Is our curve here a boundary? And why, yes, it is. Here it is. Here's our curve. Trace that thing out. Fortunately, it's a familiar one. And we can directly see that it is a boundary. It's a boundary of this surface here. Everybody on board? Yeah, question?
So, if the curve has to be a boundary,
yep.
You just said it wouldn't work on something like a sphere that doesn't have boundaries, right?
Well, in this case, we're starting off with the question being that we're looking to compute a certain line integral, right? So, if the question comes at you of, here's a curve, compute the following line integral, then yeah, your example doesn't even fit the question. See what I'm saying? Yeah. I mean, you could say vacuously, I suppose, is a compute the following line integral over the non-existent curve. But that's, it just doesn't make any sense. Yeah, it's a good question. Okay, detail. Don't forget boundaries, or the word boundary is a loaded word. It means something very particular and special about orientation. So when I say that this curve is the boundary of that surface, notice I haven't yet highlighted any statement about orientations. We've got to think through about the orientation. The curve came with an orientation, right? That you can tell just from, the way the parameterization goes. The curve came with an orientation. So we've got to think through which of our possible orientations, this one, which you might call the upward orientation, or this one, you might call the downward orientation. Which of those orientations, and you got to think about the whole thumb and swirl and side swiping, rule. Which one of those orientations on the surface gives you the correct orientation on the curve? And you just got to sit here and just kind of feel like that, right? Hand gestures. Feel free to do all of this that you want during the exam. Yes.
Technically, we don't have to use that surface.
Correct. Oh yeah. I'm going to talk about that in a moment. Yeah, absolutely. Yeah, but we're going to because this is the easiest one. Yeah. So yeah, think it through, and you can persuade yourself that this is the correct one. And again, you just got to thumb, swirl, think about which way it goes. This is the right one. That means the normal vector is 0, 0, 1. Point straight up. So, yeah. So with that having been observed, let's see. Oh, I probably should have left that there. So this being the new this surface, right? Then flux of the curl through that surface gives me the line integral of the original vector field on the boundary curve. And now it's all computation. The curl of the vector field is an algebra problem. Got to look at this vector field, take the appropriate partials. Again, you got to memorize that formula. Make sure that you're really good, proficient at cranking out curls reliably. So easy to make a sign error. So think it through. Right? And the curl in this case is 0, 0, 2. By the way, notice not 0, right? That's how you know right there that there's no anti-gradient. The curl isn't 0. Okay. And then the ds vector. Now, just because it's convenient in this case, I'm rewriting the ds vector as little n ds scalar. Point being that this happens in this case to turn the question into a convenient scalar surface integral that I can interpret as a question about area, and so life is good. It's not always going to be the case. I mean, sometimes the resulting flux integral, you might find it easiest just to parameterize the surface, perhaps, right? Sometimes you will get lucky, and this dot product might be 0, in which case you're done. Okay? Anyway, who knows? Yeah, okay, so great question about the surface. I picked this surface. Here's our curve again, by the way. I picked this surface here because I have a natural instinct towards self-preservation. And this is the easiest surface that I can pick. But you could have, I suppose, picked, for example, what I like to call a glove surface. Right? Imagine a great big glove-like thing, and where's the boundary of that glove surface? Well, it's sort of the rim of the hole you put your hand in, right? And look, sure enough, if you set it up right, yeah, the boundary of that glove is that curve. So you are welcome to use that surface. It's rarely a good idea, right? One time, I was, feeling devilish or something, and I manufactured an example where the best surface to use was not to pick the flat surface, but where the best surface to use was to pick a hemisphere. And something really nice happened algebraically. it took me some doing to figure out how to come up with such an example. And that kind of thing is not very common. It's not very natural. Vast majority of the time, pick the simplest surface, whose boundary is the given thing. Yeah. Did I see it? Yeah.
I think I figured it out.
Oh, okay.
Yeah.
Yep.
Okay.
Okay.
I'll just ask it.
Yeah, sure.
So like for the glove thing, if you change the surface, wouldn't the curve C parameters be different, and wouldn't you be changing the whole question essentially?
Well, the question was, compute a line integral around this curve, right? And I am subsequently choosing on my own, with my own free will, to view this curve as being a boundary, and I can view it as being the boundary of anything for which it is actually a boundary. Right? And so you could imagine, the flat surface, it's the boundary of that flat surface, but it's also the boundary of this hemisphere. It is also if I were to kind of take that hemisphere and kind of poke a little, protrusion out of it, it's still the boundary of that. And I could keep poking protrusions until I just make a glove. Just being silly, of course, right? No one would ever do that. Okay. I guess what I'm pointing out is you have a choice. The surface, what you might call the anti-boundary of the curve, is not unique. So you get to choose. Choose wisely. Choose lazily, I'll say. Choose selfishly. Okay. So y'all may recognize this page. Not exactly, but you may recognize the way that this picture is drawn and kind of the layout. So, in fact, here's the page you actually are probably thinking of. There was a page where we talked about how Green's theorem connects back to things that we had previously discussed in the context of the fundamental theorem of line integrals. Right? And the way we made that connection is we observed that, well, look, if you take this region here, and if you look at its boundary and look at, that point and that point, and you can think of that boundary curve then being broken up into two chunks, right? And then sort of observe what's the boundary of what, and not hard to persuade yourself that Green's theorem just says this. In the context of that picture as I've drawn that picture there. Well, the analogies between Green's theorem and Stokes' theorem are very strong. In both cases, we're computing circulation around a boundary curve, just like this picture. Right? So we went through all these details some time ago talking about Green's theorem, so I'm not going to go through these details again. But here in our new context, talking about Stokes' curl theorem, it's a surprisingly similar situation. If you have a surface in space like this, for example, right? And you can talk about these 2 points. Pick some random, doesn't even matter. Pick any 2 points on the boundary curve. You can think about that part of the curve, call that C1. Or think about this part of the curve, call that C2. Notice C1 and C2 start in the same place and end in the same place. Just like they did in this context. Notice that the boundary of S consists of both the curve C1 and the curve C2. Be careful, you're going backwards on C2. Don't forget your minus sign. Just like was the case here. So the analogies are extremely strong. It's really the same argument again, just kind of ripped off and applied to this highly analogous context. And so you get this. I'm going to say same result when you write down Stokes' curl theorem as pertains to this picture. Stokes' curl theorem tells us this. And then you can play the same clever little games. Let's think about, given this result, what would happen if the curl were 0, hypothetically? Well, if the curl were 0, that would mean that this flux is 0. Which would mean that this side of the equation is also 0, which would mean that those two line integrals are equal. And that would be true for, gosh, some exceptions. Let's not worry about anomalies, but pretty much any two curves that you can draw between those 2 points. You can find some surface in between them and draw this picture. Right? And therefore, seems plausible the vector field's path independent. Which we recall means that the vector field is a gradient. And so here's one of our, what I like to call lifetime theorems. If the curl is 0, then the vector field is a gradient. And you can turn that around backwards also. Suppose that our vector field is a gradient. Let's just say, hypothetically. If our vector field's a gradient, well, we know that means path independent. We know that means that these 2 line integrals are 0. These 2 line integrals are equal. That means that their difference is 0. That means that the other side of the equation is also 0. That's how equations work. And now, well, how could this possibly be? How could a flux integral always be 0 no matter what surface you pick? You can draw this surface anywhere, any way, and for every possible surface, you always get a flux of 0. Well, the only possible explanation is that that curl is 0. That integrand. So there's the lifetime theorem the other way. So curl being 0 means you're a gradient. Being a gradient means the curl is 0. It's crazy analogous to these arguments that we made over here in the context of Green's theorem. And I think it's a really useful idea to spend a little time, flip back and forth kind of between those pages, right? Look at and just notice how, my gosh, they are the same argument. Okay, the analogies are very helpful. Okay. Y'all remember path independence? Here it is. Path independence. We talked about this long ago. The idea is that if you fix a couple of points, if you fix a couple of points, let's say A and B, a path-independent vector field seems like a trick to be able to do this, but if you could, hypothetically, a path-independent vector field is one where if you were to compute the line integral along C1, if you were to compute the line integral along C2, just make sure that it starts and ends at the same points, then you always get the same answer. So along C1, along C2, same integral. And I like to present this, y'all may recall, a little bit dramatically. I like to say, how could this possibly be true? It seems like it's it's an infinite number of requirements because there's infinitely many different curves between C1 and C2, and the vector field therefore has got to be satisfying infinitely many requirements. It just seems intractable until you notice that, oh, well, really it's just it's a sort of an immediate consequence, or this is something that follows in the case of a special category of vector fields, gradients. Fundamental theorem of line integral says gradients always do this. And here's the argument. How do I know that these two things are equal? Well, along that first curve, how do I compute the line integral? Well, by looking at this formula that only depends on the boundary points, not the curve. And then how do I compute the line integral along this curve? Well, by the fundamental theorem of line integrals, which again only depends on the boundary points. So two curves with the same boundary points, the line integrals are going to be computed by plugging f into the same boundary points. And so of course you get the same value. And of course it's going to work for any curve that starts and ends at A and B respectively, because they're computed by the same formula every time. So all gradients have this feature of being path independent. So I hope everybody remembers this argument. So there is a analogous fact about surfaces. Right? Path independence says any two paths with the same boundary points, certain property holds. Surface independence refers to a requirement involving any two surfaces having the same boundary curves. So the picture is a little harder to draw. Here it is. Suppose my first surface, like this. Second surface, like this. Now, again, very careful. Not just any two random surfaces. They have to have the same boundary. Like so. Alright? So, surface independence says that, again, this is a remarkable feature. This is how could this possibly be true? How could this ever work out for any vector field is kind of the initial feel of it. We need to know that whenever you have two related surfaces like this, that it would always follow that the flux through the one surface is the same as the flux through the other surface. Right? And again, seems like a intractably long list of requirements. Our vector field's got to do this magic trick for every surface that has the same boundary curve, but there's bazillions of them. Right? I drew two here, but you look at that purple boundary curve, there's bazillions of surfaces that have that same boundary curve. This vector field's got to give the same flux through all of them. Right? So that is a pretty impressive property for a vector field to have, if that's the case. So, strong analogy with path independence. Again, I like to give the dramatic introduction just for kind of impact, but not only is this possible, but Stokes' curl theorem tells us a long list of vector fields that do this. And what it is curl fields. Okay, so let's think about, suppose that we were looking at a curl specifically. Let's just say we're looking at curl fields. Well, Stokes' curl theorem tells me how to compute the flux through that green surface. The flux of a curl is the circulation. Notice that circulation happens on the shared boundary. And now, what about through this bottom surface? How do I compute flux of a curl field through that bottom surface? Well, Stokes' curl theorem tells me that I compute it as a circulation, again, around our shared boundary. And you can furthermore see that any surface I pick, as long as it's got that same boundary curve, the flux of a curl can be still computed by a circulation around the exact same boundary curve, and so it's always going to be the same. Very strong analogy Very strong analogy to what we were seeing here, because we were looking at gradients. The fundamental theorem of line integrals tells us that the shared boundary is all that matters. Here, because we were looking at curl, didn't hit the button. Here, because we're looking at curls, Stokes' curl theorem tells us that the boundary is all that matters. Okay, how are we doing? Is everybody on board? Okay. Oh, wow, gosh, I hit the wrong. Sorry. Okay. There's an analogous picture that you can draw with this, same kind of idea in mind. Let's, so again, here we have this green surface, we have this blue surface. Suppose they have a shared boundary curve like that, right? Now, got to think careful about orientations. I want these two surfaces, S1 and S2, to have the same boundary. I want them to induce the same orientation then on the boundary. And so, counterintuitive though it may seem, the orientation on the green surface, that is what you're going to want to call outward, right? The orientation on the blue surface is, well, what you're going to want to call inward. And that doesn't seem right, right? Aren't they oriented kind of opposite? Well, in this way, in order to orient them such that they have the same boundary orientation, then thought of as part of the boundary of the peanut, that they enclose, right, they have this opposite sign. And so there's that minus sign. And again, we're uncomfortable. Very often we're uncomfortable with that minus sign. It kind of feels like didn't we do this backwards, right? But keep in mind, these are two different questions about boundary. You can't really compare the orientation on the orientation on the green surface and the orientation on the blue surface. They're different surfaces. There's no comparison between them. If you want to think of them in how do their boundary orientations relate, okay, but whatever. That's up to you, right? If you want to think of them as how they contribute to the boundary of the solid on the inside, well, okay, if you want to, you can do that, but again, that's your choice. There isn't really an actual comparison between those orientations. So we set it up this way for our convenience here. That minus sign is unavoidably, that's part of geometry. That's a reality of how geometry works. Okay. With this having been set up, again, just kind of stealing from our previous results, here's what Gauss's divergence theorem says. And I guess we're out of time, so I can't go through this, but you can see it coming, and I encourage you to maybe preview a little bit. Go ahead and spoiler, right? But think through what happens if the divergence is 0. You end up concluding that you have a curl, and think through what happens if the curl is 0. You end up concluding divergence is 0. And it's a lot like that. Look how strong the analogy. Oh, whoops! I'm hitting the wrong button. Look how strong the comparison is. These look just alike. Okay, good place to stop. See y'all later. Have a good Monday. And by the way, I need to check off names